This will be a short lecture to summarize the 2D nets that we have derived so far and the game plan for going forward. So let's pick a pen color here. And let's summarize how we got here. If we looked at 1 and 2-fold elements added to T, we ended up with the oblique net, or the parallelogram, the primitive parallelogram, same thing. And you recall that was T2 and T1. And in that case, the two magnitudes are not equal necessarily. Square net was produced from adding a 4-fold axis to T, and we ended up with T1 by definition equal to T2 to be a square, and the angle between the two is 90 degrees, right? 3 and 6 added to T produces hexagonal. I'm losing resolution here, so maybe I'll just won't draw it, you know it. T1 equals a T2, and T1 angle with T2. If you pick the smallest angle, it's going to be 60, but you could equally look at it as a 120. But gives you the same, at the end of the day, it gives you the same pattern. And then we had developed the rectangular. And remember, the rectangular required, of course, that not to be the square, these two could not be equal. Oh, and that was generated, by the way, that was our first generation of a mirror plane plus T, right? So we're taking these elements and we're grouping them to find out, and we're going to come back and talk about group in a second. We're grouping these in order to produce a net, the nets that are possible. So we're already forming groups, we just haven't used the terminology yet. We're going to talk about that in a little bit. So, and these guys are at right angles to each other. And, yes. And then finally, if we actually didn't put the restriction that they're perpendicular to each other, we end up with the equivalent of a centered rectangular. Now my resolution is getting really low. But the bottom line is that T1 doesn't equal T2, and they're perpendicular to each other. It's just that the difference is that one has a center rectangle, the other one doesn't, right? Okay, now let's talk a little bit about what we've actually done kind of intuitively. We've made lattices that are compatible with symmetry elements, right? And so I just want to mention that a little bit. So what is a plane group? Well, in a way, what I've just defined as our 5 lattices, we made them compatible with a translation vector. So in a way, this is already a group, right? Because what do? We took elements like 1-fold, 2-fold axis, we added it to another element, and we created, in this case, the oblique. But it is a set of elements that we could call a group. Now the question is, it has to satisfy other criterion in order to be a group. And the problem is with that lattice, it doesn't quite work. And that's because one of the criterion is you have to be able to generate one of the other elements from having operation on one of the other elements. And so I can double check that, but I'm pretty sure that the lattice lattices, that doesn't work. However, what we do have are these different symmetries that are compatible with these lattices. For example, this produced the oblique, right? Now we can come in and say, all right, fine, I can introduce elements into there and form plane groups. And the same thing I can say for let's say the square. So if we look at the square lattice, it's compatible with a fourfold symmetry. So I should be able to think about it as a group, but I can add more things in there. For example, what about mirror planes? So I could add a fourfold axis in there, but what about adding a mirror plane? So I can add more and more elements to these things, and what am I going to get? I'm going to get plane groups. So what we're essentially doing is building up from the ground. First we made the lattices, which automatically are compatible with rotation plus translation, and just write that. We did all the rotations plus translation, and then we did the mirror planes plus translation. Of course, there's more combinations in here we haven't talked about, and we're going to work on those. So there's more. You can see one right here that we didn't talk about, rotation and mirror plane, right? So those more combinations are going to produce what's called more point groups. So those are groups. They're going to have elements like rotation and mirror plane or whatever they are, and right. But when we put them in a lattice, just like we put these things in a lattice, they become plane groups because there's all these different elements. So all we're doing is finding out what kind of symmetries are compatible with each other through these simple theorems, and then we just place them in other things that we know are compatible and see if we generate uniquely new patterns or not, right? So eventually you build up to what are called plane groups, which could be called two-dimensional crystallographic space groups. It's the same thing. So again, we've kind of taken these lattices and made elements like a one-fold, two-fold axis be compatible with translation vector, and we produce all these lattices, so they're kind of a combination now. We know kind of how to fill space, in other words. And then what we're going to do is we're going to add in our elements again, and all of the elements we have so far right, but we're going to create point groups, more point groups. These are point groups, by the way. We just haven't used that term yet. And we're gonna add things like etc. And then we're going to discover by accident, but we're going to do it on purpose. We're going to discover another one called the glide operator, which is not here yet. So we're going to develop these point groups, and when we stick them in the lattice, we're going to create eventually 17 plane groups. And we'll review this again, so if this seems a little confusing. But remember, all we've been doing is trying to build up in a very didactic, implicit way instead of jumping into group theory and math and complication, right? So you see how we started with rotation plus translation in order to make that compatible with those 2, 3, 4, and 6-fold axes. And that's why we don't have 5, for example. So there's no need. If we jumped right into trying to combine all these things, we wouldn't have left out 5-fold symmetry, right? So by first creating the lattices that are compatible with rotations and translations in mirror planes and translations, now we're ready to think about more point groups that we could add in besides the ones we have in here. And then we'll start putting them together, and we'll eventually arrive at our 17 plane groups.